Hi everyone, we're doing 2.6, which is the chain rule today. So I'm just going to quickly go through this formula. If you take a look at the one at the top, if we have a function, a composite function like this that says f of x equals f of g of x in the brackets, then how we would take the derivative of something like that. So if you look at it, it's like there's an inner function and then there's also an outer function. Or you can look at it in terms of substitution to make it familiar. If we want to take the derivative of that, if you look here, we want to take the derivative here of the outer function. And we want to multiply that by the derivative of the inner function, which is this portion here. So I really do think the easiest way for us to make sense of this is to take a look at an example and actually apply this. So if in this first example it says differentiate and we have r of t equals root 5t minus 8, then the first thing I want to do is, again, I like to do the whole organization approach. So if we want to go through this, I'm going to say that my f of t, so my outer function, so think outside and then work our way in, would be a root or a radical function. So I'm going to make it just root t. And then if I want to make this clear, my g of t would be the inner function, the one that fits into that root t, and that would be this 5t minus 8. So you're starting to get a sense of, it's kind of like working backwards from when we first learned substitution. So basically think big picture, start with the outside and work your way in to get some organization with this. And then I like to take that same approach as what I did with you last day, which is to take the derivative of both of them so that it's super clear for us, and then we can bring it all back together to make this easier to work with. So we know that this is like saying t to the 1/2. So the derivative of this would be 1/2 t to the negative 1/2. And we know from practicing this quite a bit that the best way for us to write that is 1/2 root t. So that's the same thing as 1/2 t to the negative 1/2, just to remind you. And if you're unclear, unsure, hit pause. Try it out yourselves actually to apply the power rule and deal with the fractional exponent. But I think you'll find that you're okay with this, hopefully. Okay, so we're done with the derivative for that. Let's do the same thing by taking the derivative of our inner function. So the derivative of this, when we look at it, we know it's just a constant, which is 5 in this case. Okay, so now that we have all the different parts, we can put the whole thing together to find the derivative of this bigger or the entire function. So we can say, I'll just do it down here, r prime of t equals, I'm going to put the therefore symbol there. I don't know if I've been using that much, but you've seen it before. And then we would have, again, just to make it super clear, we'd have f prime of g of t times g prime of t. So that's our general way that we would write it. So that's just me applying this formula up here. And then when we actually take the different components and put them together in here, what that means is we would get, so again, if I'm looking big picture, I want this 1/2 root t. So I'm going to say that this is the same thing as saying 1/2 root t. But what was my t that went under the root sign? It's actually 5t minus 8. So 5t minus 8, which was this part here, to remind you, is the part that gets plugged in. Okay, and then that's going to be times g prime of t, which we found from up here, is just equal to this constant, 5. So the only part I want to sort of clarify and draw your attention to, I feel, is this part here. So yeah, we would do f prime. Notice this is not f prime of t. This is f prime of g of t. This was f prime of t. What that is saying is what your g of t is. So this part here is what got plugged into here and here. So I feel like that's maybe the only part, especially if you're learning it remotely by yourselves, that might cause you a little bit of confusion. So I hope that that helps to bring some clarity. And then our final step to put this all together is, of course, we like to check to see if we can simplify anything top to bottom, and we can't. So we just get 5 at the top over 2 root, and it would be 5t minus 8, which is what was down here, and that is our r prime of t. So after all of this, that's going to be our final answer that we're working with. Okay, so I hope that that made sense and that you're okay with that. And let's move on to one more example that takes on a slightly different form. So I'm going to slide that out of the way. And actually, I'm going to get rid of that so it's nice and clean. If we look at this, we have f of t equals t squared minus 2 over t cubed, all to the power of 2. So I want to show you a slightly different approach. We can do it the same way as what we just did back there, or there's another approach that you might find easier to work with. So I am going to start with saying this. We are going to use substitution. I am going to let u equal all the stuff that's in here. And I've basically just chosen a different variable to make things easier. So t squared minus 2 over t cubed is what I'm making the inner function, to refer back to the same terms I used in the last example. Okay, and I'm going to just say y equals f of t, which is this part here, which is also just equal to u squared, if we're going to look at the bigger picture. And I guess to clarify that a bit, I mean like that whole thing there. Okay, so we're basically just using substitution, calling these different things in order to simplify it a little bit. And then I'm going to use this notation that we haven't used quite as much. We usually use y prime or f prime of t. But remember, I introduced this to you on the first day, dy dt. So again, the derivative of y with respect to t, because we're dealing with this in function notation where everything is with respect to t, would be equal to the derivative of u with respect to t, which is du dt, times dy du. So let me sort of show you what's going on here. This, if you look at it, there's a du at the top and a du at the bottom. So technically they would cancel and end up just giving this dy over dt. This is just a different notation or different way of writing it or saying exactly the same thing. So I want to get you familiar with this notation. So I'm using this to sort of show you both methods. You could do this all using f prime of t like we did in the last example. Okay, so knowing that, let's go through this and let's work our way through all of this. Okay, so if we want to get du dt, let's do this. So let me work my way through that. If we want du dt, what that is saying, to make this clear, is we want to take the derivative of this part here. So derivative of the first part, we know we would get 2t, and it's just the 1 at the top, so we don't need to worry about that, minus, we can take the derivative of this part separately. So to make it easier, notice that this is like saying t to the negative 3. So it'd be like 2t to the negative 3. So when we work our way through this, we actually end up with a plus 6 over t to the 4 when we're just applying our power rule. So I had brought the t3 up to make it t to the negative 3, which would then make it t to the negative 4 and pushed it to the bottom. So again, if you're unsure, hit pause, do that yourself with this portion here to make sure that you understand that when you apply the power rule by moving this back up to the top, this is in fact what you get. Okay, so we get that, and we want dy du. So now I'm just taking the derivative of this part here. Sorry, I got rid of that there, which is just going to be equal to 2u. So again, we're doing the same thing as what we did in the last example. It's just taking on a slightly different form with this notation and this notation that we're now using instead of u prime and y prime. Okay, so we always put this back together once we go through it. So I'm going to do this again. Therefore, our dy dt, so the derivative of y with respect to t, or y prime, would be equal to what we found here. So our, well, I guess I should color code it. Our 2t plus 6 over t to the 4 times our dy du, which was our 2u. Okay, so I want to go back to this for a second to show you. Remember that I had written it out in this format, so dy dt. So this is just basically what we have done. And you know what? I should probably do this, dy du, so that you are able to clearly see where it's coming from, just to color code it. So that's what we have filled in here, just to make it super clear. And then, we're not quite done yet, we just want to make sure that we distribute these and clean things up to leave it in our final answer in an appropriate form. So our dy dt, which, let's make this thicker so it's easier for you to see, would be equal to, what's the best way for us to do this? Well, first of all, do you see that our u was equal to all of this stuff here? So we need to take that and plug that back in. So here, where I have my 2u, well, u is t squared minus 2 over t cubed. So when I go through all of this, I'm going to move this 2 to the front and just sort of shove it off to the side. And then I have this portion here that we had already talked about, 2t plus 6 over t to the 4. So that would be this part here. And then I want to plug back in what my u value was up here. So that would be this portion here. I'm going to plug that back into here. So here I have t squared minus 2 over t cubed. So I'm wondering if I can shrink that down so you can see all of it. Hopefully you're able to see all of it so you can see where it comes from. But after working our way through all of this, that's what this would simplify to. And what I have been telling you is that I know that some of you might decide to multiply this all out and simplify it. Some of you might choose to leave it in this form. I don't really care. I want to give you the freedom and flexibility to choose the form that you want to leave it in. What I am doing on quizzes and tests is I will give a number, like I will say find dy dt when t is equal to 1, for example. So you plug in a number and you can spit out a numerical value, which allows you to have some freedom.